Chris Wallis. I'm a rendering engineer at the Coalition. I'll be talking about how we use Tier 2 variable rate shading on the Xbox Series X and PC. Here's a quick rundown of how this talk looks. I'll first introduce what variable rate shading is, why we care about it. I'll go into our implementation in Gears 5 and Tactics. We'll show some of the results on both the visuals and the performance improvements. And then finally, we'll go over some integration tips to help others evaluate if variable rate shading makes sense for their engine. So before we get into any kind of technical detail, I wanted to motivate why we even care about variable rate shading. So this is a screenshot of a jungle level from the Hivebusters campaign in Gears 5. On the Xbox Series X, the whole campaign runs at 4K at 60 FPS. And to me, this scene really represents why we want full 4K. There's just so much great water and foliage detail that benefits from a high resolution. That said, we added lots of expensive effects for Xbox Series X, such as our full PC Ultra graphics quality settings and green space global illumination. 4K is very expensive, and it's worth taking a step back and asking, does everything really need to be 4K? If we look at these shadowed regions on the rock, it's quite dark and more difficult to pick up details. It's not that we can't notice the detail, but perceptually we know the eye has a harder time picking up things in darker areas. If we look in these areas in the background, we can notice the scene starts to look cloudy, becoming almost invisible due to the volumetric fog. And finally, it's important to keep in mind the water here is translucent, so we're rendering loads of opaque geometry underneath that water. What's important to keep in mind is that while both fog and translucency are obscuring the scene behind it, we're still running all the usual expensive passes on that geometry, like screen space ambient occlusion and screen space global illumination. And so you can see, even for a scene like this that's dense with detail, there's still a reasonably long list that don't really need to be at full 4K. What we really want is some kind of tool that lets us control resolution, but in very limited areas of the screen, while leaving other areas untouched. And that's exactly what variable rate shading does. It allows you to specify the resolution of a pixel shader with various ways of controlling where you apply that reduced resolution. So by default, there are 4 types of shading rates. There's 1x1, which is full resolution. There's half resolution horizontally, half resolution vertically, and then finally just half res in both dimensions. There's also optional shading rates that are only supported by some hardware, or even coarser shading rates. We didn't use these in our implementation due to the smaller hardware support, but it's worth pointing out that these exist. We actually shipped Tier 1 Vrs support with the release of Gears Tactics on PC. Tier 1 is a more limited version of variable rate shading that's quite coarse and requires you to specify a shading rate on a per draw granularity. What that means is you essentially select a single shading rate per mesh. The benefit of Tier 1 is it has a wider range of hardware support. One of the priorities for Gears Tactics was the ability to run on even low-end Intel integrated parts. And we found simply relying on dynamic resolution was a poor experience. By using VRS, we were able to get better control of how to tweak resolution and to give a better experience even on integrated GPUs. That said, it wasn't without compromises. Even the more conservative uses of VRS were still noticeable due to the lack of fine-grained control. So fast forward to the Xbox Series X and S. For Gears 5, we wanted a next-gen experience that could leverage the power of RDNA 2. We also added new visual features such as contact shadows, screen space global illumination, but all of these were really taxing on the GPU, even for the beefy Xbox Series X. We wanted to make sure dynamic resolution could stay high without compromising visuals. Variable rate shading was interesting, but as a flagship platform, we really didn't want to make any visual compromises. So this is where Tier 2 variable rate shading comes in. This allows you to decouple shading rate from geometry by instead specifying that shading rate in a screen space texture. This texture isn't one-to-one with the final render target, but a coarser tile size of either 8x8 or 16x16, depending on the hardware. On the right, you can see what this would look like with 8x8 tiles from Pix. And finally, this is a debug visualization of Vrs Tier 1 versus Tier 2 applied on Gears Tactics. The colored regions are areas where coarser shading rates are being applied. As you can see here, Tier 1 is blocky, and on conservative settings, it's really only applied to a limited amount of things in the background. With Tier 2, it has a much higher granularity, and its adaptive nature is allowing it to selectively apply variable rate shading to individual small bricks on the road, where you can see it can even get into there on the smaller dark cracks that really the Tier 1 couldn't touch. All right, so let's talk about the implementation of that. The overall pipeline is relatively small. The implementation relies on using information from the previous frame to determine which pixels on the current frame can be rendered at a coarser resolution. Fundamentally, there's 3 steps. First, we generate a Vrs texture using the final color buffer from the previous frame. Next, we run a rescale shader to count for dynamic resolution, as well as reprojecting things to the new frame. And then finally, we bind that Vrs texture to any applicable passes. So let's dig into each of these steps. The edge detection is really the meat of a Vrs implementation. We implemented a simple Sobel edge detection filter in a compute shader. We map a compute shader thread for every pixel in the full 4K buffer, with the thread group size matching the hardware Vrs tile size. Each pixel then uses edge detection both vertically and horizontally to calculate a shading rate. It's important to call out that this should be done in sRGB color space, since what we care about is the perceptual difference between colors. A configurable threshold value is passed into the shader that determines what meets the bar for a coarser shading rate, which is the primary mechanism we use to tune different quality settings on PC. At the end, you can use a quick wave op to get the lowest shading rate for that tile. One of the biggest issues we hit with this initial approach is that generating the Vrs texture is slow. At 4K, it costed 0.4 milliseconds, which is a lot to pay for something that's supposed to be just saving you time. So here's a couple of the key optimizations we used. First, we skip border pixels on your tile. So by the D3D spec, a 2x2 coarser shading rate is not allowed to straddle the border of a Vrs tile. And so by skipping that border, if you just do the math on that for a 8x8 tile, you can cut down pixels you need to do edge detection on from 64 to 36. And that by itself halved the time to 0.2 milliseconds. At that point, we looked at the bottlenecks, and you spend a lot of time. We had this, our edge detection running at the very end of our post-processing chain as a standalone compute shader. And so we looked at the bottlenecks there, and most of our time was spent just writing out the scene color and then immediately reading it back in the edge detection shader. So a quick trick we did was just merge the edge detection into the tone mapping shader and avoid that round trip to memory. And then the final optimization we did was just running on an async compute over our next frame's depth pass. The rescale shader then takes the output Vrs texture from the previous frame and rescales it to work with the downscaled dynamic resolution if necessary. The rescale shader is extremely lightweight because it's running on an 8 to 16x downscale of your render target. So it's quite fast. We also do the reprojection here, and we largely do this here because unlike TAA, you can get away with an approximate reprojection because worst case here is you'll get a single frame of reduced resolution in an area of fast movement. Again, in practice, we didn't see any artifacts due to just the approximated reprojection. And finally, the easy part, binding the Vrs texture. This is made easy in DX12. Just call it RS set shading rate image and pass in the Vrs texture. We applied Vrs to more than just the base pass, but also to many of the other heavy-hitting passes like lighting and screen space reflections. One thing we found was that applying to Vrs to some passes is more obvious than others. For example, translucency, which is usually used for things like dust or mist, generally have low-frequency textures, and you can get away with a more aggressive use of Vrs. However, something like screen space reflections ends up being a lot more noticeable. And so to handle this, we ended up generating 2 different Vrs textures, our default Vrs texture and a more conservative Vrs texture. The good news is generating the Vrs texture is largely free. We reuse the edge detection results, but just compare against a more conservative threshold value. Because the shading rates only use 4 bits in an R8 texture, we can store the conservative shading rate in the upper bits of the texture, and then we split shading rates into separate textures as part of the rescale shader. So let's go back to that screen space global illumination pass I hinted at. Screen space global illumination defaults to firing 8 random rays per pixels to different areas of the screen to approximate indirect lighting. Visually, it has great results as you can get lighting off of things like emissive objects that would generally be too expensive to represent as light sources. But it's also easily the most expensive effect that we had on Gears 5. Global illumination generally tends to take well to being done at lower resolutions, so VRS seemed like an interesting idea. The problem here is that it's a compute shader, and VRS only works with the fixed function rasterization. But that's okay. The Vrs texture can be read from in a compute shader just like any other texture. The screen space global illumination shader is a bit of an oddball where a single thread group has 4 waves. So we adapt that to work with VRS by using the shading rate and terminating some of those waves based on the shading rate. So a shading rate of 2 by 2, for example, would terminate 3 out of 4 waves. And then at the end of the shader, we fill in the holes for the waves that were terminated. So let's get into the results. This is a screenshot of Gears 5 with VRS off. And this is VRS on. So I'll go back and forth between those a couple of times. But I won't spend too much time here because there's really nothing here to see. I've scrutinized these myself, and there's virtually no difference. So this example is a little more interesting. This is a shot from a cinematic in Gears 5. This is VRS off, and then this is VRS on. And here you actually will notice some subtle difference in the bokeh. And this is because VRS is being used quite aggressively here because it's detecting that the depth of field is blurring out a lot of detail in the background. But what's interesting here, I'll go back and forth, is that I want to draw your attention to the fur on Kate's armor. And in this case, it actually looks a little bit better with VRS on. And that's largely because we're seeing an almost 10% increase in dynamic resolution scaling. And that really shows up with things like alpha masked fur and hair. So here's a quick look at a breakdown of the performance on that frame on the Xbox Series X. On the right, you can see a visualization of where VRS is being applied, with the red areas being done at full resolution. Yellow is either half vertically or half horizontal, and then green is full half resolution. As you can see, past performance can scale quite differently based on different performance characteristics of a pass. Switching gears, let's talk about PC. On PC, we offer 3 different VRS settings: quality, balance, and performance. So quality matches what we use on console. The target here is really 0 perceptual difference from VRS off. Balance makes some minor trade-offs that are noticeable if you're just flickering back and forth between screenshots. But in general, it's largely not noticeable, but you get a bigger perf gain. And then performance mode is visually noticeable, but still relatively minor, but gets the biggest GPU performance increase. On the bottom right, you can see a visual comparison of how aggressively it's applying shading rates. I took these performance numbers on an AMD RX 6900 XT on the Ultra settings, but I should note that we saw very similar numbers on NVIDIA RTX cards. That said, clearly the PC Ultra settings are kind of too easy for the 6900, as we're hitting way below 60 or way above 60 FPS. And so let's look at our PC Insane settings, and we'll also turn on screen space global illumination. As you can see, the performance gain from VRS is quite a bit bigger. And this makes sense because we have much heavier shaders, and so you'll see larger gains from VRS. So finally, I wanted to talk about things that will help you evaluate A, if VRS is worth pursuing, and B, how much work is involved. For performance, the good news is it's very easy to evaluate this. Using Tier 1 VRS, you can simply set everything to use 2x2 shading rate at the start of every command list and see how that changes performance. This is the kind of thing I would expect even for most engines. It'll probably take you less than a day to test out. And my suggestion would be taking that final performance gain and consider your final win to be something between 30 to 50% of those savings. I wanted to note that you shouldn't be looking at the whole frame performance time, but specifically of passes where VRS would make sense. So for example, your VRS texture is generated from the point of view from your camera. So if you're doing anything, say, from a lights point of view, it really doesn't make sense to be applying VRS there. This is a simple trick we use to apply VRS to passes. Essentially, we added a scoped VRS class that would apply Tier 2 VRS on construction and unbind it on destruction. This made adding VRS to passes largely a one-liner. Note that the VRS mode here is just a toggle that we use to determine whether it should use the normal VRS texture or the conservative one. And then finally, I wanted to go over a few bugs that fell out of VRS. Every engine is different, so I hope this gives you a sampling of some of the issues you might hit so you can kind of estimate them out that would be involved integrating into your engine. So the first of these is the fact that Unreal Engine, its material system uses a node-based system that allows artists to largely program the materials. And this is largely fine. VRS usually doesn't need to care, but the one case it does is the use of the DDX and DDY material nodes. Essentially, these material nodes correspond to the DDX and DDY HLSL intrinsic. And the problem here is that when VRS is used, it actually will stretch your derivatives when you're going to half res. And artists probably won't expect that. And so the solution here is pretty easy. Essentially, you can either correct your DDX to be as if there was no VRX. In our case, due to patching reasons, we couldn't do that. And so instead, we just ended up disabling VRS for any materials using these nodes. The next is to be wary of passes that rely on dithering patterns between pixels. The SSR implementation in Unreal Engine relies on dithering the direction of rays within a 4x4 pixel block to handle glossy reflections. And when 2x2 shading rate was used, it effectively turned that dither into a 2x2 pixel block, which ended up looking quite poor. The fix here was pretty simple. We simply just needed to make the SSR shader VRS aware by stretching that dither pattern across an 8x8 pixel block instead when 2x2 shading rate is used to ensure we still get nice glossy reflections. And then for lighting, so this is an example of where VRS was causing odd specular highlights to show up where you wouldn't expect it. So it's a little hard to see here, but essentially if you look on the bottom of Kate's amulet, there was a couple of sort of specular hot spots where you wouldn't expect it to be because it's in shadow. And the issue here, if you look at the normal gbuffer, it's kind of obvious what's going on where essentially 2x2 VRS is being used on the edge of that mesh. And when you use 2x2, the pixel centroid moves to the center of that 2x2 block. And you end up interpolating the normal on that edge. And so this can be problematic because the interpolated normal doesn't really represent either of those things. And so the solution here is again, pretty straightforward where instead of putting your pixel centroid at the center of your 2x2, you want to snap it to one of the pixels in that 2x2 block. And then finally, a common question we get is whether any special handling is needed for HDR. Theoretically, the answer is yes. In practice, we don't. So Gears 5 and Tactics were both authored in SDR, and then we convert to HDR in a final post-processing step. That mapping is based on a curve generated from a machine learning algorithm, as well as heavy amounts of artistic tuning added on top of that. Which is really all to say that the mapping from SDR to HDR is not a linear conversion. And in theory, VRS should be applied differently between SDR and HDR. However, we found that applying VRS based on the HDR results were good enough. We didn't notice any kind of weirdness with HDR. And a benefit to treating SDR and HDR the same is that we got a consistency in performance that wouldn't change, so we didn't need to kind of double our testing for both SDR and HDR. So to wrap up, if there's one way you take away, and one thing you take away from this, it's that VRS is a tool that can make your games look better. It's really easy to see it as a feature that strictly reduces resolution. But when it's used in tandem with dynamic resolution, it gives you a much better control over where you spend your GPU time and ultimately a higher quality frame. I'm a big fan of the way the VRS API was designed. With a lot of GPU optimizations, they're kind of a gamble. We don't really necessarily have a crystal ball to tell us, which optimizations might work out and which won't. With VRS, you can use Tier 1 to pretty quickly assess what kind of performance gains you might be able to get. And then finally, since this is all using DX12 Ultimate, this means any work you do with VRS will carry over across both console and PC. And with that, I just wanted to give some thanks. I wanted to give some thanks to the key contributors. So both Jacob Nelson and Cam worked on the VRS Tier 1 implementation on Gears Tactics. And then the rendering team that helped out on the Gears 5 implementation. And then finally, the tech art, who were kind of largely they made the call on whether this met the visual bar. And then some help from the Xbox, D3D, and ATG folks. Finally, here's some references on some of the blog posts on VRS. And with that, thanks for watching, and hope you have enjoy the rest of the GameStack Live Talks. Thanks.